Okay. Let's see. So our aldehyde group can be turned into a hydrazone. There is a point here. So technically we could add an additional one. So say we converted this carbon and we added another one of these. Oh my goodness. This has a special name, which I think might be the most important thing for you to know. This is referred to as an Osa zone. So when you have two hydrazones added to your saccharide. Was there anything else that you remember him focusing on for this one? So essentially, our saccharide has phenyl hydrazones added to it. If you add two of them, it becomes an Osa zone. Okay. The next one, cyclic acetals. I'm not great at drawing the geometrically true cyclic, so I'm going to just stick with my hexagons. But technically, these are how the rings would really look. This is a reference point. So here we have our hemiacetal in its cyclic form. But sometimes your neighboring OH groups might decide to bond together. So here we form our acetal. Oh wait, I'm sorry, that's not. It's too simple. So here we have an OR group, here we have our other R group, OR group. There is a note here. So this process can occur as a protecting group. Okay, so cyclic acetals can be used as a protecting group for hydroxyl groups. I think this section is the hardest section of this chapter, because we just talked about monosaccharides. Now we're going into disaccharides and polysaccharides, but the vast majority of this information you should have received at some point in general chemistry. So I think most of the new stuff we've actually completed.
So those are cyclic ethers.
Cyclic acetals.
So under her notes it says they're linked as cyclic ethers.
Interesting. I mean, technically, well, I mean, there are two adjacent ether groups, but that in and of itself isn't acetal. I would just be careful with that terminology.
Okay.
I'm not saying that this is technically, I'm sure this is technically right, but on a test, I would be careful putting cyclic ethers. Okay? So for disaccharides, Okay, we know that we're talking about two sugars. There are a wide variety of disaccharides, but it seems like he's only focusing on one, sucrose. Sucrose is the sugar that people put in coffee and, you know, what you would consider table sugar. What two monosaccharides is sucrose made out of?
Glucose and fructose.
Good, glucose and fructose. I'm going to show you how glucose and fructose are linked in sucrose, but I'm also going to show you another pretty common disaccharide just to show you the difference. So if we were to look at, say, maltose. This is two glucoses linked together. Okay, so we have just another reference point because I don't know how in-depth he went. When you're numbering carbons, you always start with the anomeric carbon and you work your way clockwise. So 1, 2, 3, 4, 5, 6. Okay, so here we have the anomeric 1 carbon linked with carbon number 4. Okay, you tend to see this a lot. 1,4 bonds are pretty common. On the other hand, so here's our glucose. Fructose is a furanose, so it's a 5-membered ring. It still has 6 carbons, but instead of our typical OH group here, we have that CH2OH. Okay, so our acetal bridge looks like this. Okay, so if we are numbering these carbons, we have our anomeric carbon here, anomeric carbon here. So we actually, this is technically a 1, 2, because this would be considered the 1 here. But the point is we have two anomeric carbons linked together. Would you, knowing this, do you think that sucrose is a reducing sugar or not a reducing sugar?
No.
Not a reducing sugar. Whereas if we look over here, maltose, so while one anomeric carbon does have an acetal linkage, one glucose doesn't. So technically this ring is free to open and close as it pleases. So this glucose ring could open up and could be oxidized.
So it's if two anomeric carbons are linked together.
Exactly.
It's not reducing sugar.
Exactly. The only way to break this acetal bridge is to hydrolyze it in acid. Okay, so you can when you add acid to this, the acetal bridge is broken, and you actually form, I mean, Dr. Cosper's notes shows it the best, but you actually form 4 different types of monosaccharides. And the 4 different types comes from the fact that we can have alpha-beta glucose and we can have alpha-beta, well, Can't even say that. It's a little bit more complicated. This ring structure can be organized a little bit to be 5-membered or 6-membered. But that's where the 4 different monosaccharides come from. The 4 different monosaccharides are referred to as invert sugars. So I would know that. So sucrose is not a reducing sugar because both anomeric carbons are in that glycosidic bond. You can break that bond by hydrolyzing it with acid. This causes 4 different monosaccharides to form, making sucrose an invert sugar. Oh wait, sorry, not sucrose. The four products are considered invert sugars, sorry. Any questions on sucrose? All right. So the last piece is our polysaccharides. There are technically 4 different polysaccharides that you talked about. Do you remember any of them?
Starch.
Okay.
Cellulose.
Okay. There are technically 2 different types of starch. They both start with A.
Amylase.
Mm-hmm.
Amylopectin.
Good.
How did you remember that?
I don't know, because I think it sounds fun to say.
I don't even know how I got amylase. I don't know where I pulled that from.
Well, be careful with your ending there. So you just said amylase. That's actually the enzyme that breaks down amylose. He'd probably give you credit for that, but OSE is the sugar, ASE is the enzyme. But good. Doesn't matter where you got it, right? Just make sure you get it on the quiz too. There's one more here though. What's the starch analog in animals?
Glycogen.
Very good. Okay. So there are really 4 different things that you should know for each of these. So this really lends itself to a chart. I wish I had better markers.
Do you want to try that marker?
Try any marker.
This is ridiculous.
What happens at the end of the semester though? 'Cause it's like, do you want to order more markers for like 2 weeks? I'm just gonna sit around all summer. Okay, slightly better. Okay, so the first thing you should know is where these are found. Okay, and it's really, are they in plants or are they in animals? So cellulose, plants or animals?
Plants.
Starch, both types? Plants. And I already gave this to you because I called it the starch analog in animals, so this one is in animals. Okay, function. We talked a little bit about this at the very, very beginning. So the 2 main functions of starch, there are other ones, of course, it's very versatile, but energy storage and structure. Okay, so those are really your 2 options here. So cellulose, do you think that cellulose provides energy or is it more for structure? Structure. This is what gives plants rigidity. Amylose, amylopectin.
Energy.
Energy, yeah. And glycogen?
Energy.
Energy. Good with that? Okay. I'm going to call this main linkage. Okay, so how, oh, I didn't say this before. I'm sure he mentioned it. So all of these polysaccharides are polymers of glucose. So essentially you have repeating units of glucose in all of these. Which makes sense if we're talking about energy, right? Because glucose is our main source of energy. So you don't have to worry about knowing what monosaccharides are in here. You already know it. They're all glucose. What is important is how those glucoses are linked together. And that does change a little bit. So I didn't really go over this. I don't know how much he went over it in class. So you can have, do either of you remember how you would talk about linkages? Or how you might name them?
Like 1,4.
Good, yes. So that's one piece of it, right? What carbons are linked together. The other piece is whether it's an alpha linkage or a beta linkage.
Oh, yeah.
Okay? So technically a glycosidic bond would be alpha or beta with the number. So alpha 1,6, for example.
And then its name, right?
Yeah, you could go just call glycosidic bond at this point.
Oh, okay.
Yeah. So from lecture or maybe from previous experience, do you guys remember any specifics about any of these types of linkages?
Weren't most of them, well, you already said, like 1,4?
Yes. They're actually all 1,4, so I'll give you that.
Okay.
So that's one thing you don't really have to worry about. What you do have to worry about is what's alpha and what's beta. I'll give you a hint. So enzymes in humans can only break down alpha glycosidic bonds. So which one of these have to be alpha? Because we know that we eat them.
Glycogen.
Glycogen. Anything else? Do we eat starch? Yeah, we eat a lot of starch. I eat a lot of starch. So both amylose and amylopectin have alpha 1,4. So that's your pasta, that's your rice, it's, all of our favorite foods. So the one that's not is beta. And it also makes sense if it's giving it structure. So that's why things like celery don't really have much nutritional value for humans. It's lots of cellulose. So if we boil down the main linkage into what you really need to know, all of them have the same numbers. I don't know if he's even going to ask you about the numbers. But cellulose is the only one that's beta. Everything else is alpha. And know that beta means that humans can't break it down. So we don't get any energy when we eat cellulose. The last piece you should know is whether this has branching or not. And if it does, what kind of linkage is that? We'll talk about that too. So what do I mean by branching? So we know this is a bunch of glucoses linked together. Okay, so if we're talking about something that doesn't have branching, it would have, let's say, 25 units of glucose all linked together in one straight line. When you do have branching, it looks like this. Okay, so we see a branch coming off and then we have another chain starting up here. So you can get multiple chains coming off of this main chain. So that's what I'm talking about when I say branching. Any thoughts on why this might be, no, we're not going to talk about that. Any ideas which of these polysaccharides does have branching or doesn't have branching?
So would cellulose have branching?
It would not. Good guess, though.
Well, isn't it harder to break down if it has branching?
Not necessarily, because the branching, if we look, this is really the same exact structure as this. So if we have one enzyme that is really good at breaking this bond, it would be just as good at breaking this bond. Granted, you have maybe more branches, but that doesn't necessarily mean that it is harder to break down. It's really the same process. It just might have to be repeated a few more times. Really what this, in terms of efficiency, this is actually a better structure if you're trying to get energy from something. So for example, we have, multiple branches coming off at different points. And we want to break this down to get energy from it. If we had just one single chain, we could only have one enzyme working on it at a time, breaking one bond at a time. If we have multiple branches, that means we can have an enzyme here, breaking it down, an enzyme here, breaking it down, here, and here. So we could have 4 enzymes, technically on the same molecule, breaking down that molecule to get energy from it. So this is more efficient in terms of getting energy from something. So cellulose does not have branching. One of these starches, so amylose or amylopectin, doesn't have branching either. So amylose does not have branching. So amylopectin and glycogen are the ones that do have branching. And they have the same types of linkages as well. And I actually gave you a hint here. So I drew it the exact way that it's linked. So this is our glycosidic bond, okay? And we number the carbons, so we have 1, 2, 3, 4, 5, 6, and this is 1, okay? The O is in a downward orientation, okay? So it's an alpha 1,6 glycosidic bond. Does everybody see that? Okay. Would any of these polysaccharides be considered reducing sugars?
Not amylopectin.
Okay.
Glycogen.
So I would be careful. I know I drew it above, just like I did with fructose, but sucrose. But remember, this is not the anomeric carbon.
Oh,
Okay, but you're on the right track. So my one issue with this is this chain has to end somewhere, right? So technically, you might expect there to be an OH group eventually. With this, due to the size of it, I also don't know if it's always acetylized on one end, but none of these are considered reducing sugars, because all of these anomeric carbons in the middle are acetylized. Okay. So none of these would be considered reducing sugars. So the one disaccharide we talked about, all of the polysaccharides we talked about, would not be considered reducing sugars. Fructose, even though it is a ketose, can be reorganized into an aldose. So I would just assume that pretty much any non-acetylized monosaccharide, so any monosaccharide that can open and close, I would assume that that can be a reducing sugar. Okay? Do it on time. Only an hour. I didn't think it would take that long. Any questions on polysaccharides or anything that I might have gone too quickly through? Do you want to learn a fun fact about sticky rice?
About what?
Sticky rice?
What's
Do you guys know what sticky rice is?
No.
What? You guys don't eat sushi?
No.
No.
Oh my goodness. Okay. So the rice that's used in sushi is called sticky rice. Okay. Because it has to really stick together to hold its shape. So I learned in I think it was general chemistry actually, that sticky rice is made up entirely of amylose. So most of the time starches are a mixture of both, but sticky rice has been genetically, modified over the years to contain only amylose. And so that's why it actually sticks together so nicely. The branching would actually impede that interaction between the molecules. Obviously the wrong audience to tell that truth. That fun fact too.
Sorry to disappoint.
That's okay. I'll excuse it this time.